You may remember that before we looked at electrical circuits, we saw LR-series circuits and RC-series circuits. Because I is dq dt, in the LR-series circuit where we have L di dt plus Ri equals E of t, that Ri is actually R dq dt. In the RC-series circuit, we have R dq dt plus 1 over Cq is equal to E of t, but that R dq dt is I. Maybe I forgot to say LR would have an inductor and a resistor, and an RC would have a resistor and a capacitor. If we've got a circuit that's got an inductor, a resistor, and a capacitor, then all of the voltage drops in the circuit, represented on the left side of an equation, equal the impressed voltage on the right side. So we combine the L di dt plus Ri, which is the same as R dq dt, plus 1 over Cq to get E of t. And that gives us our model for an LRC series circuit. Since I is dq dt, its derivative is the second derivative of q with respect to time. And so the LRC series circuit has the model L d2q dt2 plus R dq dt plus 1 over Cq equals E of t. Underdamped, critically damped, and overdamped have the same meanings as for spring mass systems. They arise in the same ways. That is, whether the auxiliary equation has 2 real roots, 1 repeated root, or imaginary roots. And the complementary function of the equation is the transient term or solution. The particular solution is the steady state solution. Now, it may seem like there's a lot to remember with these circuits, but really it's your second order model. You need to remember which one gets L and R, and that the capacitor, it shows up in the equation as 1 over C. But you're generally given what you need, at least in this course. Find the charge on the capacitor in an LRC series circuit when the inductance L is equal to 1/4 of a Henry, the resistance R is equal to 20 ohms, the capacitance is 1 over 300 farads, and the impressed voltage is 0. We have initial conditions. Q of 0 is equal to 4 coulombs, and I of 0 is equal to 0 amps. And then we're asked if the charge on the capacitor is ever equal to 0. This is pretty straightforward. 1/4 dq dt, which I'll write as q double prime, plus 20 q prime, plus 1 over 300, that's going to be 300 q is equal to 0. Clearing the fraction and then writing down the auxiliary equation, factoring it, gives us roots of m equals -20 and -60. So q as a function of time is c1 e to the -20t plus c2 e to the -60t. Since q of 0 is equal to 4, we get that c1 plus c2 is equal to 4. We have information about I of 0, it's 0, but for that we need I, which is the derivative of q. So I of t is -20 c1 e to the -20t minus 60 c2 e to the -60t. And then bringing in that second initial condition, I of 0 is equal to 0 is going to imply that -20 c1 minus 60 c2 is equal to 0. We now have a system of equations. C1 plus C2 equals 4. -20 C1 minus 60 C2 is equal to 0. Solving the system is going to give us that C1 is equal to 6 and C2 is -2. Our model is then Q of t is equal to 6 e to the -20t minus 2 e to the -60t. That function answers the part, find the charge on the capacitor. So that's part of what we're looking for. Circle it because we're really proud of it. And then we're asked, is the charge on the capacitor ever equal to 0? So that question is, does Q of t ever equal 0? Setting Q equal to 0 and solving the resulting equation yields t equals 1 over 40 natural log of 1/3. But that natural log of 1/3 is negative, and I'm going to say this whole situation started at t equals 0. So my answer would be that the charge is never 0 for a positive time value.